evening and welcome to Tinkering with Edkelar. It is time for a smaller project again, or two, or three. As anybody who is dabbing into hobby electronics knows, there is one piece of equipment that still cannot be replaced in prototyping: the humble breadboard. Now, while there's quite a few levels of quality around, one form factor has been dominating ever since the ancient days of yore. An arrangement of 5-pin strips between some bus bars set up to accept DIP ICs and similar pin headers. Of course, I also have a few of them around. So besides good contacts on the inside, what makes a good breadboard if they are all the same? It must be the accessories around it. And here's where I fell into a rabbit hole of epic proportions. There are countless kits available, usually designed for educational scenarios, so they have a small desktop footprint. Let's have a peek. Over here we have a common, simple solution: a breadboard next to some banana plugs. These can be used to make connecting a power source to the circuit a bit easier without disturbing the arrangement on the board. The upside is that it is easy to put aside an idea and later reconnect it. The downside is that it is not really self-contained and always needs external devices to go, so disconnecting and reconnecting can become a bit of a chore in itself. A similar, yet more specialized solution is what I call a carrier board. It combines a breadboard with some other established tinkering devices. This one I have here is made for the Raspberry Pi and an Arduino Mega. I use it for all my digital tinkering needs. Note that I also glued on a power supply board, which can take up to 12 volt via a barrel jack connector or a 5 volt USB input, to provide regulated 5 volts or 3.3 volts to the breadboard. Normally, these power adapter boards plug into the breadboard and take up some space. I hardwired this one into the power rails. Now, what to do with analog circuits? When you need symmetric voltages for amplifiers, for example, this model here got you covered. It's an E&L CDP-01. Besides the obligatory 5 volts, it offers regulated plus/minus 15 volts and unregulated plus/minus 24 volts. And for good measure, 10 volt AC too. The regulated voltages can be put in low and high power mode, which limits the current at different levels. It also has a sliding potentiometer and 2 toggle switches for your input needs. The next one I got here is the E&L CD1. Same manufacturer as the previous one. They made quite a bunch of these. Check out Curious Mark's channel for a few larger models even. While this one only has one breadboard, it does come with a built-in clock generator and offers some nice connectivity points to hook up scopes or meters. The supply voltage can be switched from the usual 5 volts, TTL, to a variable 3 to 15 volts for CMOS chips. Note the little metal tab on the supply switch that a teacher might use to lock the supply to 5 volts. And now to this model. It's made by HP, the Logic Lab 5035T. Apparently, it was part of a larger educational bundle with a load of ICs, wires and a manual. But I only found the board. If the manual is available somewhere, please let me know. At any rate, it comes with a 5 volt supply, 4 LEDs, 6 switches and a clock generator for 100 kHz or 1 Hz. The 5 volts are available on the rear too to power external stuff. But for some reason, HP uses BNC connectors for those. Must have been a phase. They had the same on the 1600 logic analyzers for probe power. And now to the restoration of the different models. For narrative purposes, let's start with the HP model. It arrived in good condition, but you probably know the motto: don't turn it on, take it apart. And while I can't claim credit for the phrasing, I do live by it. The case comes apart easy enough. The inside consists of a small mains transformer, a line voltage selector, and a PCB underneath the breadboard. Nothing else. The circuit board contains both the mains voltage switch and the TTL logic, with some separation, but one has to be careful when handling it. In typical HP manner, there is also a service manual with it. Let's look at the circuit. The circuit is simple, but it does show that the LEDs are buffered, so current draw is minimal and they will react to proper TTL levels. The switches are also routed via a clocked flip-flop. The clock is derived from the clock generator, and so the chip will only switch the output over ever so often. Interesting way of debouncing switches. The 100 kHz clock is made from a simple oscillator, while the 1 Hz version is also interesting. It gets the clock input from the AC output of the transformer. HP relies on the chip, protected with a resistor, to turn that into a 50 or 60 Hz TTL input clock, and then has a switch to select between divide by 50 or 60 to get the 1 Hz output. Finally, the 5 volt is created from a simple 7805 and a few capacitors. Speaking of capacitors, the main filter one will be replaced as per usual protocol. The rubber cover was a bit sticky on the PCB, not sure if aging rubber or escaped electrolyte. The other capacitors are tantalums which measure fine, so I'll keep them. To clean up the top cover of the case, I wanted to remove the breadboard first. But when I carefully pried at it, it started moving in a weird way. Turns out that this thing has a hidden surprise. The breadboards are glued to a metal sheet and there's 2 magnetic strips underneath. These have a slanted edge on one side, so pushing down on the lower end will pop up the upper end for easy removal. I love that solution. putting the PCB back in place. And giving it a try. Yep, checks out. Up next on the bench, the CDP-01. It arrived with Velcro-style covering instead of breadboards. Apparently, it was to easily swap out one circuit for another, similar to the HP. I can see that useful in a school environment. Every student has their own breadboard, and during class they get the box and work with it. I like that idea too, but I like the HP magnet approach better, so I'll remove the pads. The inside was a bit more classic, I dare say simple. There's a PCB with the voltage regulation. The unregulated DC voltage isn't current limited, so there's fuses in here instead. One was blown. The AC output taps directly off from the transformer output, not even a fuse in this one. The transformer is interesting. It has two primaries which are connected in parallel. This should be easy to convert to 240 volts. The 5-volt supply seems to have a trimmer, the other doesn't. So plus minus 15 volt is regulated and stable, but only close enough. The power switch turns out to be an off-off switch. Needs some cleaning. putting the two primaries in series for the 240 volts and giving it a slow wind-up try with the Variac. Why so careful? Well, the coils need to be wired correctly. If the connection is putting one coil in reverse, the magnetic fields would fight each other. Mathematically, they'd be cancelling each other out, but physically, I'd at least expect some angry hum. After recapping, I reconnect everything, making sure that the heatsinks are not shorting out, and give it a try. Again, a dab of thermal paste can't hurt, even though there are insulator pads. The 5-volt rail was a bit off at first, but the trimmer made sure that it is now spot on. Works. Now to the breadboards. I got myself a stash of plain ones and cut a piece of sheet metal into matching sizes. With the breadboards glued to those, it is time to add magnetic strips to the box. Nice! I like it! Sturdy, yet it comes off in a bit more predictable way than the Velcro would have. Note that the sheet metal is a bit too thin for the HP push-to-pop method, but they also fit in good enough. The CD1 model is probably the one with the most interesting look, but it's a bit worn. The banana plugs are tarnished to a charcoal color, and the case is a bit dirty. Yikes! I thought this case was dirty on the outside. Sheesh, has this been in a flood? The transformer is tiny, but it would be enough for the task. Let's see how much voltage we need. 8 volt AC? That is unexpected. How does it make 15 volt output from that? Darn, no schematics available online, and the dual layer PCB has a black solder mask. I only decoded the first part of the power supply to find out how the transformer ties into the 15 volt supply. It seems they made a voltage doubler of sorts by using the big electrolytics in it between the rectification diodes. I didn't follow all the traces for time reasons, but that explains quite a bit. Is that higher component count really cheaper than a slightly higher voltage transformer would be? Vishal gets some serious scrubbing. I tried to do the recapping in situ, but the cover plate and some of the knobs are too dirty to be cleaned in place. So I need to desolder the connecting wires first. For the banana sockets I had almost exact replacements in stock. Just blue and yellow instead of blue and white. Close enough. The first of the logic input switches is already half open. I think it must have suffered a bump from above. One of the rectifier diodes was clearly a replacement, so I replaced them too while I'm at it, so that all four are the same again. Cleanup time! Let's start with the potentiometer. Yikes! Oh my god! I've seen all sorts of potentiometers, linear, logarithmic, center tapped, wire wound, but I never had one that could be measured in grit. I'd say 180 grit. What a mess! But it's working again. Now I better get all the other items. I got a hunch the switches might look similar. Power switch first. I also replaced the limiting resistor for the neon indicator with double the original value. The clock selection switches needed a bit of fresh grease, but was in surprisingly good condition otherwise. I found a transformer that claims to output 8 volts from 220 volts, but it's originally DIN rail mount. Let's see if I can use that. Oh, the raw transformer has a very similar form factor than the original one. I will try to reuse the mounting bracket with the replacement one. Needs a bit of adjustment, but it does fit. Recapping again, Since the replacement transformer provides a bit more than 8 volts, I'll also up their voltages. 25 instead of 16 and 50 instead of 35 should do the trick. Again, axial ones are hard to get these days, so I need to be creative. New thermal paste for the regulation transistors. I wanted to replace the power cable, that's why I cut it originally, but I don't have anything in stock, so I'll reuse it anyhow. Assembling the lot. I'm also converting this one to magnetic strips, so the included breadboard can go. Need new screws though. and some troubleshooting is in order. The 5-volt rail looks a bit uneven. There's clearly a bit of the mains frequency overlaid. After a bit of poking and prodding, I realized that one of the electrolytics got really hot. I triple-checked the polarity, and yes, it was soldered in correctly. But when I put the scope on it, it showed negative charge anyhow. Turns out that the one diode that was already different and repaired before was busted again. Strange. I put in a new one, 4007 this time, and it worked. For about 2 minutes. Now the other diode is busted and the next capacitor sees negative voltage. Sheesh. I replaced all 4 diodes with 4007s and the bulging cap is also binned. One of these sockets, the leftmost switch, is busted. The inner spring part is missing. So until I get a fitting replacement, this has to stay almost complete, sadly. And here we are, portable circuits. And that's it. I might get a few more of these breadboard kits for the collection, if they become available. I hope you enjoyed this multi-project episode. See you next time! Good evening. This is going to be interesting.